Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Stefan Neuhaus, who is right now a postdoc at the University of Trento in Italy. Stefan did his PhD at Saarland University in German with his advisors Andreas Steller and Michael Backes. And so Stefan will today tell us a bit about a study that he did on Red Hat Linux. So please, go ahead.
Thank you very much. Yeah, as Tom already said, I want to talk to you today about some research that I've been doing together with Tom. And the results of this study that I'm going to talk about have been published or will be published at this year's Usenix. So we're talking about a Linux system called Red Hat. And when you install Red Hat on your computer, you may get the idea that Red Hat is basically one big monolithic operating system. But in fact, that's not true. Red Hat consists internally of quite a number of so-called packages that you can install, also download individually. And there are about 3,241 packages by August 2008 that were being offered by Red Hat for Red Hat. Of course, there will be a number of third-party vendors that will also offer packages for Red Hat. We have only counted those that were offered by Red Hat. Now, each of those packages may be vulnerable, may have vulnerabilities, software flaws that can lead to security errors. And the reason why this is, yes? Yes?
So what do you define as a vulnerability?
Sorry?
What do you define as a vulnerability?
I'm coming to that. And the reason why this is important is that fixing vulnerabilities is costly, or having vulnerabilities in deployed software is also costly. There's a study by the FBI from 2005 that estimates the total cost to the US economy alone due to software security flaws at $67 billion in 2005. So that's quite a lot of money. And so how do we assign vulnerabilities to these packages? So what usually happens is that somebody will discover a flaw and exploit it probably. And then those people at Red Hat, they will issue what is known as a Red Hat Security Advisory, also known as an RHSA for short. And they will say, okay, in this case, for example, it says that there has been a flaw discovered in a package called XPDF, and there's an update necessary because of that. And how do we know this when we downloaded the data? Well, we look at the rest of this security update, and we find the package name here, and there we can see the XPDF package name, and so we can say, okay, this package has now one vulnerability. And in this way, we continue until we arrive at a picture that may look something like this in an idealized way. And when we actually do this for Red Hat, we arrive at this distribution. There are a few interesting things about this. The first interesting thing is that about 2/3 of the packages, please note that the y-axis is logarithmic, so it's not a linear scale here. The first thing that we notice that about 2/3 of all packages do not have any vulnerabilities at all. They have never been implicated in any security incident. The second thing that we notice is that most of the packages have only a very few vulnerabilities. So we have about 300 packages here that have one vulnerability and have never been implicated in any more vulnerabilities. But we also have a number of packages that have quite a number of vulnerabilities. The biggest one is kernel with 129 security patches for it. And also because the documentation for the kernel is synchronously updated with the kernel, it also technically counts as vulnerable. And we also have here a number of packages which are all PHP related. So PHP is obviously also has been implicated in quite a number of vulnerabilities. And when we have such a graph like this, and if we put ourselves in the maintainer for Red Hat with a limited number of resources, we can ask ourselves 3 questions. The first question is, are there any features in those packages that correlate with vulnerabilities, that would make it easy for us to see, okay, this is a package that looks like this, and it has a feature that correlates with a vulnerability, so it may be profitable to look at. The second question is, are there maybe features that can increase or perhaps even decrease the risk? So if we make a new package and we can choose the features, maybe in a limited sense, can we maybe choose features that will decrease the risk that we face? And the third question is, when I have a package that has no known vulnerabilities, are there ways to predict whether it does, but I just don't know about them? And in the remainder of the talk, I will show, yes, indeed, there are features that correlate with vulnerabilities. And these are a package's dependencies. Second question, also, yes, we can find that with formal concept analysis, which I will explain later. And we can also predict whether a package will contain unknown vulnerabilities, also using dependencies with machine learning. But before I go into the technicalities of this, I'll just very briefly talk about dependencies of a package. So when we have a package like, in this case, Amanda Server, which is a backup program, this package you cannot download and install the package on an empty computer. You need to have other packages installed before you can install Amanda Server. One of those packages is the C runtime library. This is a simple thing because Amanda is actually written in C, so it will need the C runtime library, and therefore the package that contains this runtime library will have to be installed before you can install Amanda Server. So that's a very easy one, but there are a number of other packages that you have to install before you can install Amanda Server. Now, so this is a very small extract of the whole dependency graph within Red Hat. The question is, why do we think beforehand, a priori, that dependency might correlate or might have anything to do with vulnerabilities? Well, dependencies exist because a package wants to use the services that are being offered by another package. And therefore, we can make a connection between those and a vulnerability in A if, for example, A is part of an insecure domain. For example, web browsers form an insecure domain, in the sense that web browsers are often the targets of attacks and they often succeed. And related domains, or the packages inside the same domain, tend to have the same dependencies because they do the same functions. Another way that a vulnerability can exist in a package is that if the dependency is insecure and the fix in the insecure dependency somehow spills over to the original package. For example, if there is a fix in a library and that fix entails an API change, then the program that uses the library will also have to change. Or it may be that the dependency is difficult to use securely. There is one example that I'm not going to show later where, for example, SSH is found to be quite insecure, whereas other security libraries are not. So here we have the complete dependency graph, and as you can see, it's quite a ball of string. If you do this in any other layout, it will become even less informative. For example, if you try to draw it in a hierarchical fashion, you have a very few nodes at the top, and then you have a very broad thing in the middle, and that's it. So this is the thing, actually the representation where you can see the most. But when you just count how many dependencies packages have, you get another statistical graph like this. And you can see that also it's actually very nice. It looks very much like it looks very much like an exponential distribution with a long tail, which I suppose it is. And you have packages that have a staggering 96 dependencies. So you have to install 96 other packages before you can install KDE base. And on the other hand, you have packages that don't depend on any other package, which are basically, most of the time, these are either documentation packages or development packages that contain header files, which are just text and don't depend on anything. You had a question?
So when you calculate dependencies, do you include like the transitive closure?
No. These are just the direct dependencies. So this is why this is even more stunning.
Yeah.
It's 96 direct dependencies. Otherwise, you can't install KDE base. This is really quite a lot. So the first two questions, are there features that correlate with vulnerabilities, and are there features that can increase or decrease the risk? So basically what we want to do what do we mean when we say, are there features that increase or decrease the risk? Well, what we mean is when we add dependencies, when we go to packages that have more dependencies than other dependencies, and we look at packages that have one more dependency, does the risk go up or down? So where does the addition of dependencies significantly increase or decrease the risk? And for that, we need three things, basically. We first need a data structure that will allow us to work with that question, which is, in our case, a concept lattice, which I will talk about later. Then, in the next step, we will have to compute the change in risk as we go from one set of packages with one set of dependencies to another set of packages that contains one more dependency. And in the third step, we will only include significant changes and then see what happens. So, first step, we need a data structure. Our data structure is going to be a concept lattice. So first, we start with all the packages. We take a look at the risk in all the packages. And then, in the next step, we take a look at the packages that depend, for example, on glibc. And of course, by exclusion, there are also packages that do not depend on glibc. For example, all the packages that have no dependencies at all. There may also be packages that depend on KDE-libs. There may also be packages that depend both on glibc and KDE-libs, of course. In the next step, we look at packages that depend only on glibc and Qt. And in the final then in a step, we look at packages that depend on glibc, Qt, and Xorg X11 libs. And because this is a lattice and not a tree, this kind of edge is also possible. So we can have packages that depend on KDE libs and Xorg 11 libs. And now there's a technique called formal concept analysis that will create for us this graph if we just give it the dependencies. So there's a technique that will give us this. Now in the next step, we will have to see what risk do we have when we go from one node in this graph to the next node. So we will have to take a look at the numbers. And as I said, about 1/3 of all packages are vulnerable. This is what this means. So when I know nothing about a package's dependencies, my best guess is 33% vulnerable, 2/3 non-vulnerable. Now, when I additionally know that the package also depends on glibc, the vulnerability rises by a little bit. And these two numbers here, this number is going to be less than this number, and this number is going to be less than this number. And so as I go down this lattice, I will get different percentages. And the question is, when I label these, the question is, so I know that when I know that a package depends on glibc, the risk increases by 0.6% over when I know nothing about the package. The question is this significant, statistically significant? This is the next question. Or when I go from packages that depend on glibc to packages that depend, where I know that they depend on glibc and Qt, the risk rises by quite a staggering 43.9%. And the question here is, this is the risk change by adding Qt only when I know already that they depend on glibc. For example, when I know, when I have packages that depend on Qt but nothing else, I would have an edge from here to here. So, and now that we have this graph, we need to include only those that are statistically significant. And we do that by employing statistical cat tests, either a chi-square test or what is known as a Fisher exact test. And we include risk changes only when they are statistically significant at the 1% level. That means that a change this high will be observed by chance in only 1% of the cases or less. And when I have no significant and more general context for this dependency. And when the risk goes up when I add the dependency, I call that a beast. And when the risk goes down, we call it a beauty. And there are a few interesting, these are just a few of the beasts that we have found. The complete list can be found in the paper. And what you can find, for example, that all the packages that depend on OpenOffice.org.core have at one time or another had a security vulnerability. This is one interesting thing that you can see here. Another interesting thing is that KDE and Qt, which basically belong together, will also increase risk by quite a high amount. And another thing that you can see in the top, I think 25 or so, is that Kerberos is also apparently not easy to use securely, because packages that depended on Kerberos have had a risk increase by 43%. Now, what about the others? What about those packages where the risk goes down, what we call the beauties? Now, interesting here, you have GNOME libs. And if you write a package, if you write an application for GNOME, and you depend on glibc and zlib, your risk goes down by 17.5%. Now compare this to Qt and KDE. So I don't know if you know this, but KDE and GNOME are the competing window managers for Linux. So you can make a rational argument that one is perhaps better than the other. And you can also see that Python programs seem to be quite okay. So these are the beauties that some of the beauties that we found. As I said, the complete list can be found in the paper. Now, for the third question, can we predict whether a package has unknown vulnerabilities? And we want to ask two questions here. We want to ask, is it possible to predict from the dependencies which packages are vulnerable or not? So this is basically a yes-no question. It's a classification problem. But we also want to know which packages will have the most vulnerabilities. So we want to make a ranking of packages. This is called a regression problem. And for this, we use machine learning. And in order to experiment or to evaluate our approaches, whether they are good, we make experiments. And we do them like this. When we have a big matrix with our dependencies and we have a vector with our vulnerabilities, we split them in 2-1 ratio, so 2/3, 1/3. And then we use the bigger set to train some statistical model, and we get a model F out of this. And then we use the remaining portion to test. We input this in the model, and we get something that may or may not have anything to do with what we know is true. So then in the last step, then we compare those two, and basically the more similar they are, the better the model is. And what kind of indicators do we have? Well, first, for classification, we have two indicators called precision and recall. Precision has to do with false positive rate, and recall has to do with the false negative rate. Both are numbers between 0 and 1, and numbers near 1 are better. So higher numbers are better than lower numbers. And for regression, we have something called the correlation coefficient, which is a number between -1 and 1. And when predicted values and actual values have the same ranking, the correlation coefficient will be 1. When they are completely every which way, the correlation coefficient will be close to 0. And when they're just the opposite, the correlation coefficient will be -1. So it's a number between -1 and 1. And numbers near 0 are bad, and numbers to any kind of the extreme are good. So what we want is numbers near +1, but numbers near -1 would also be okay, because then we can just invert the ranking and have numbers near +1. So that would be okay. And so we did that with our data set. And we created 50 random splits, 2/3, 1/3. And we created models and did this kind of prediction, first for classification. And we used two different kinds of machine learning. The first algorithm was a support vector machine. And the second algorithm was a decision tree. And we use decision trees because they are much easier to interpret by humans than what comes out of a support vector machine. And this is the diagram that we have. So what you can see is they both, so the triangles are for the decision tree and the circles are for the support vector machine. What you can see is they both have quite high precision, but you can also see that the recall for the decision tree is much lower than the recall for the support vector machines. And also, in fact, if you make circles around these, they don't touch. And statistical analysis reveals that, in fact, decision trees are statistically significantly worse than SVMs, both in terms of precision and in terms of recall. So we don't look at this anymore. And we take a look only at the support vector machines. And what we can see here that we have a precision, a median precision of 83%. That means if I make a prediction, if I say this package is going to be vulnerable, we're going to be correct 83% of the time. This is quite high. This is quite a high number. Also, you can see that the recall is about 2/3. That means we find just about 2/3 of all vulnerable packages. Now, when you take a look at ranking, when we rank the packages, we also have quite a good situation here. We have a median correlation coefficient of just about 0.58, which is a medium to strong correlation. And the blue strip here is one standard deviation to either side. So it is a very narrow strip. That means our predictions are quite consistent. So, but now the thing is that we use this data basically on itself. So we have a big block of data where we know the values, and we split it, and we train it, and we compare. But more interesting would be to see, okay, now we take a model at some point in time and predict packages for packages that have no known vulnerabilities, and then wait half a year and then see whether our predictions were correct. And this is in fact what we did. We took the packages as they were and the dependencies as they were on the 1st of January 2008. We predicted out of those packages that had no known vulnerabilities, we predicted a ranking for them. So we show here only the top 25, but there are about 2,156 more packages below that we do not show. And then we waited half a year. Well, in fact, we waited 9 months. And then we actually took a look. And I can tell you that out of those 2,156 packages, out of which we show 25, 73 have become vulnerable. And I would like you to make a guess. Make a guess. Which ones? These packages all had no vulnerabilities at the 1st of January 2008. And by August 31, some of them may or may not have new vulnerabilities. So make a guess. What do you think? So if you can also ask me, some of the names are really obscure, so you can try to ask me whether I know.
Do you have any vulnerabilities
No.
as of January 1?
No.
So do you want us to guess a percentage?
Sorry?
Do you want us to guess a percentage?
No. Just guess packages.
Oh.
So which package do you think?
Happy, so it means all of them.
Yeah.
No. That would be very cool, but that's unfortunately not true.
75 to 80%. 75 to 80%?
Wait, there's a Python one in there. That can't be right.
Make a guess. Which, for example, do you think Torah has had vulnerabilities?
I have no idea what that.
Okay. So what happens is that out of those 25, at the time we published the paper, 9 had vulnerabilities and 1 more was patched recently. So we have 10 out of our top 25. And those 10, by the way, are out of those 73. So that's pretty good. So what can we learn from this? We can learn what could the consequences be of an approach, of a statistical approach like this. So first, when building new applications, you can choose to a degree what dependencies you will have. So you can try to choose less risky dependencies. This will come out of the formal concept analysis. For example, you could use simple authentication and session layer from GNU instead of from Cyrus, because Cyrus turns out to be a beast. Or when you maintain existing applications, you can try to prioritize your resources. For example, if you know that something like Kerberos is going to be vulnerable, you should look at that and look at not at gkermit, which is probably not a very vulnerable application. So to conclude, what do we have? We've shown that vulnerabilities actually correlate with dependencies. I've shown how to identify dependencies that are particularly risky, or that may, in fact, lower your risk, if you're lucky, and that our prediction models work with a high precision recall and correlation. And that concludes my talk. Thank you very much. Are there any questions?
Have you discussed these with actually the developers?
Sorry? Who?
Have you discussed these results with the Red Hat Linux people?
No.
The engineers? So
No. Oh, sorry, with Red Hat?
Yeah.
Yes. We've been in contact with them. And actually they did patch one package that we found vulnerable because of that. Yes. And in fact, some of the information came directly from Red Hat, and the entire research wouldn't have been possible without their help. They were very generous. Mm-hmm.
So how do you explain the correlations that you found?
I tried to hint on this on one of the early slides. We found similar correlations when we looked not at dependencies between packages, but at the include statements in C programs. So they also correlate in the same way, not as good as this one, not with as high precision and recall, but they correlate basically in the same way with vulnerabilities. And one of the ideas is, and we actually took a look at this in some detail. And what we found was that there are basically two kinds of vulnerabilities that will show up in this kind of analysis. And this is, the first kind is where the dependency is fixed. So there's a bug in the dependency, a vulnerability in the dependency that gets fixed. And for some reason, some API changes or the usage changes so that the thing that depends on it also needs to be changed. That is the one basic thing. And the other thing is that some libraries or some applications may be very difficult to use in a secure manner. So if you depend on something that is hard to use in a good way, then you will tend to have more vulnerabilities than otherwise. So these are basically the main ideas that we have on this.
In the first case, it has nothing to do with the package intrinsically, but rather with the fact that the package changes. And you could just measure, you just look at, try to do impact analysis whenever it changes.
Yeah, but not all changes are because of security vulnerabilities. And also, it may not only be API changes, which of course you have to change it, otherwise it doesn't compile or it doesn't work at all. It may also be, for example, we did a study on Mozilla, and they decided at some point to change something in the string routines. So every call site had to be changed, not because the API changed, but because the precondition changed in the API. So that's not as simple as that. It's not just a simple impact analysis. So you don't, because you have to see whether it has the change that you make in the dependency has security impact.
Okay.
Mm-hmm.
So I'm more familiar with Debian than Red Hat, but I think there's some.
I assume the results will be similar.
Okay, yeah. Well, so my question is, I know that in Debian, when I install, there's kind of this base set of core packages,
Mm-hmm.
and then there's another set of still official packages, but that aren't normally put on the machine
Mm-hmm.
at first. You have to.
Yes.
And I would expect that the packages that are installed in the base set are simply installed on more computers, and thus more vulnerabilities are going to be found. Does such a thing as like the base set next to it exist in Red Hat? And did you do any correlation, or did you see any difference, or did we investigate
So
it?
there exists a base set, yes, that's true. But unfortunately, we do not have any information about download numbers. We asked Red Hat, but there is simply no way to find out which packages run on how many computers.
You could still just make an assumption that you could create these two sets and look at the difference between them, right?
That's true.
And just assume that one's probably like an order of magnitude more often used
Yeah.
than the other.
That's right. Yeah, but we didn't do that. Yes. But as I said, we try to go the easy route and ask them, do you know how often this package is downloaded? But they don't have the information. There's no way to get it.
Okay.
So where does the paper appear?
On Usenix next week.
Okay.
Any further questions?
So that's fine, Stefan.
Thank you.